Today we are going to talk about Kafka rebalance. Before we talk about what is rebalance in Kafka, we should first gain an intuition of what is rebalance. Rebalance is not just a Kafka problem, it's inherent to any load balancing problem. What is load balancing? You have a number of workloads and you want to evenly distribute the workload to a number of workers. In a production system, the number of workloads and the number of workers can keep changing. So anytime if one of them change, the balance of workload is broken. You need to restore the balance, hence rebalance. So that is rebalancing in an abstract way. Then what is rebalance in Kafka? To understand what is rebalance in Kafka, you need to understand what are the workloads and who are the workers. There are also different kinds of rebalance in Kafka. One is consumer side and one is broker side. To fully understand these concepts, we need to clarify some terms. So next, we'll revise the main concepts in Kafka, do a little Kafka 101. Then we'll talk about the types of rebalance in Kafka and what are their consequences. To end off, we'll talk about can we even avoid rebalance at all? I believe even if you are an application developer who do not maintain a Kafka cluster, this video is still useful for you. It's always helpful to peek just a little bit under the hood to see what's going on. Okay, let's now revise the Kafka concepts. On a high level, you have producer, broker, and consumer. As an application developer, you are working with the producer client and the consumer client. As for the broker side, if you are deploying on-premise, most likely your SRE team is maintaining the Kafka cluster. If you are using one of the cloud vendors, they are the people who maintain your Kafka cluster. Let's now look at the broker in a logical view. Topic is the collection of all your messages. To make it simple, in this video, let's assume there's only one topic. Topic is broken into partitions. A partition is the unit of data distribution. Partition not only helps to split data in a logical way, also helps to split the data on a physical level. Assuming we have partition 0, 1, and 2, they belong to a physical cluster. This cluster has 3 brokers, broker 0, 1, and 2. Each broker is one machine that runs Kafka. Each of them is responsible for a partition. To increase fault tolerance, data is replicated, so the partitions are replicated. Assuming we have a replicate factor of 3, meaning each data is stored in 3 copies, our P0, the partition 0, is going to be present in all the machines. Of the 3 copies, only one broker will be the leader, the other 2 will be the follower. In this case, our broker 0 is the leader for partition 0. It is the follower for partition 1 and 2. Leader is responsible for accepting writes, meaning accepting requests from the producer because the producer writes. Leader can also accept reads, which come from the consumer. The follower can also be configured to receive read, but follower cannot accept writes. Let's look inside a partition for a little more detail. Producer clients sends messages to our topic, which end up in one of the partitions. The unique identifier of a message is called an offset. This is the identifier for Kafka, not for the application. Messages arrive into a partition in order. The earlier message have a slower offset, the later message have a higher offset. So in our P0, message 0 arrived first, then message 1 and message 2. In reality, messages arrive in batches. This is to increase throughput. Similarly, from the consumer side, consumers consume messages by batches. And here, to make it simple, we just label message one by one. If your message does not have any message key, then your message will fall into each partition in round-robin fashion. Typically, round-robin may not be what you want because you want to enforce some sort of order for some of your messages. If that's the case, you can define a message key on your message. Messages with the same key will always go to the same partition. Under the hood, Kafka will hash your message key to some number and mod that number by the number of partitions. As long as you send the same message key, it will always hash the same number and always hash the same partition. Kafka guarantees order within a partition, not across partition. Sometimes there can be a skew in the number of messages in a partition. For example, in this P2, we have 1 million messages. That can be because you chose a very bad hash function or because you have a very imbalanced distribution in your keys. So make sure you design the message key properly to avoid hot partition. And now let me remove producer from this equation because producer side is not very interesting. It is the consumer side and the broker side that's more relevant. Let's take a look at the consumer side. We have 3 consumers, consumer 0, 1, and 2. They all belong to a consumer group. Each consumer is a different machine and consume from a partition. A consumer can consume from multiple partitions. To keep it simple, in our example, it only consumes from one partition. What's the point of consumer group? The motivation for different consumer groups is to consume the same message independently. A typical use case is your team produce messages to a topic, and there are multiple teams in your company who want to consume your messages. So one message needs to be consumed multiple times. So they need to be consumed independently so we configure different consumer groups. Now let's talk about how is message delivered from the Kafka broker to the consumer. On a high level, there are 2 models, push and pull model. Push model means the broker is responsible for pushing message to the consumer. Pull model means the consumer is responsible for pulling message from the broker. And Kafka uses the pull model. There are pros and cons for both approaches. Generally, in a pulled system, consumers may get overwhelmed when the rate of production is too high. On the other side, if you have a pull model, consumers just pull messages at your own pace. And just for comparison, RabbitMQ is another popular message queue in the industry, and MessageMQ uses push model, and Kafka uses pull model. Let's briefly look at the consumer code in Java. The consumer API is called poll, P-O-L-L, instead of pull, P-U-L-L, but it's the same thing. The code structure is you will start an infinite loop and call the poll API to get one batch of records. Infinite loop because if I'm a consumer, my job is to stay here and keep getting records. Once I finish processing my batch, I would commit the offset, telling the Kafka broker, I'm done processing this batch, give me the next batch. It's not advisable to put very expensive logic in your consumer. If processing of this batch takes too long, longer than a configured timeout, the Kafka broker may think that you are dead and trigger a rebalance. Here I quote from the book. Keep in mind if poll is not invoked for longer than a timeout, consumer will be considered dead and evicted from the consumer group. Another thing is, synchronous commit here is very important because you only commit the offset after you finish processing the batch. What happens, your consumer crashes when you're processing. Say you have 10 records, you finish processing 5, then you crash. See, the thing is, you have not committed this offset. You only committed the last poll offset. So when your server restarts, you can repoll this current batch. The downside is, for your first messages that you already consumed, it will be duplicate. So it is your application code's responsibility to deduplicate. Coming back to this diagram, let's take a look at consumer 2. It's calling the poll API from partition number 2. The current committed offset is 1. This is managed by Kafka. It's trying to poll a batch size of 4, so it is going to get the next 4 records, 2, 3, 4, and 5, fetched to the consumer side. If the processing is successful, consumer 2 is going to commit offset 5 and move this pointer to here, right? But the thing is, when you're processing 2, 3, 4, 5, if you crash in the middle, maybe you already processed 2 and 3, this is still fine, because when your server restarts, the committed offset is still 1. So your next poll still give you 2, 3, 4, 5. The downside is 2, 3 is going to be duplicate. But the consequence of duplicate message is much less than losing message, because losing message is disastrous. I hope you liked that little Kafka 101. With all those knowledge, we are finally ready to talk about rebalance. First, we're going to talk about consumer-induced rebalance. Looking at this picture, what are the units of work and who are the workers? The unit of work are the partitions, right? So here in this topic, we have 3 partitions. This work needs to be evenly distributed to our workers, who are the consumers. Now, anytime your number of work change, meaning you add partition, reduce partition, or your number of consumers change, maybe one of your consumers died, or you're doing rolling deployment on your consumer, or you want to add consumer machines, that also triggers rebalance. Now, I have a question for you. Do you think consumer changes more often or partition changes more often? The number of topic partitions should be fairly static for the lifetime of an application. The number of partitions is a configuration change, and changes in consumers should be more often, because consumer machines die and get added all the time. It is somewhat risky to change the number of partitions of a topic on production. The reason is, when you change the number of partitions, you change the hash distribution of the keys on your producer side. So you just broke the invariant that message of the same key always go to the same partition. I quote from Confluent co-founder, "When you publish a keyed message, Kafka maps the message to a partition based on the hash of the key. This guarantees the message within the same key always route the same partition, so that guarantees order in the partition. If your number of partition changes, you just broke this guarantee, you broke the invariant." So how many partitions should you set? Bear in mind, number of partitions is also a unit of parallelism, meaning the more partitions you have, the more throughput you have. So initially, people would over-partition a little bit, determine a future target, say 1 to 2 years later. Typically, production traffic increases over time, so people over-provision partitions to make it future-proof, so that you don't have to constantly adjust your number of partitions. I've talked enough on why partitions configuration tends to stay constant. Now let's talk about consumer-induced rebalance. The trigger is a change in consumer group membership. It can be your consumer instance timed out, you do deployment on your consumer machines, you try to scale up, scale down. then we need to move partition ownership from one consumer to another. Speaking of partition ownership, how is a partition assigned to a consumer? I'm going to quote from the book. How does the process of assigning partitions to consumers work? First, a consumer needs to join a consumer group. It joins the group by requesting to the group coordinator. Group coordinator is one of the brokers, that is the point of contact for this entire consumer group. Consumers maintain membership in the consumer group by sending heartbeats to one of the Kafka broker designated as a coordinator. As long as you keep sending heartbeats, you are alive. The first consumer to join the consumer group is called the group leader. So group leader is from the consumer side. The leader knows all the consumers in the consumer group because the group coordinator told them. And the leader is responsible for assigning partitions to the consumer. This may or may not be surprising to you. Group coordinator does not assign partitions. It is the group leader that assigns partitions. The benefit is it allows partition assignment strategy to be pluggable on the client side, so that each consumer groups can have their own partition assignment strategy. So let's talk about a common partition assignment strategy. If you have the book, you can go to the partition assignment strategy section. A common strategy is sticky. Think of it as a round-robin strategy with something more. What is that something more? In the case of a rebalance, it will leave as many assignments as the same as possible to minimize the movement of assignments. Meaning when you need to rebalance, minimize the change sets before and after, hence sticky. If we look at this diagram, you have the cluster on the left and consumers on the right. We have two consumer groups. Consumer 0 has 3 consumers. This consumer 0's point of contact is one of the brokers. So broker 0 is the group coordinator responsible for consumer group 0. And broker 1 is the point of contact for consumer group 1. And all the consumers in consumer group 0 want to join the group by chit-chatting with the group coordinator. Consumer 0 happens to join the group first, so consumer 0 becomes the group leader. And group coordinator will inform him who are all the members. Then consumer 0 will assign partitions to all the consumers in the consumer group. Once each consumer knows which partition is supposed to consume from, it will contact the corresponding brokers with that partition. Now that you understand how are partitions assigned to consumers, let's talk about what happens in the rebalance. I highly recommend this article from Confluent. Before I talk about the rebalancing strategy, let's think what requirement must rebalancing satisfy. We need to guarantee that no partition can be owned by more than one consumer at the same time. Partition can only be owned by one, not more than one. Now, why is that? There are all sorts of problems when you have multiple consumers on the same partition. You break the order, you broke the exactly once message delivery guarantee on the consumer side, because one message is supposed to be consumed only once. You commit offset that's lower than before, so we need to guarantee that a partition is only owned by one consumer at the same time. But the thing is, in a distributed system, at the same time may not be simple. So to keep things simple, the eager rebalancing protocol is born. So this is the naive rebalancing protocol. When you want to do rebalance, all the members will quit the group. If you look at the diagram over here, all of them quit the group, then all of them rejoin the group. So here you avoid the race conditions, but there is a period of unavailability. No member of the group can do any work during the rebalance. As an enhancement to the eager protocol, the incremental cooperative protocol is born. The problem with the eager protocol is every consumer give up all the partitions, but in reality, some partitions do not have to be rebalanced. Then don't give them up. Revoke as per necessary. The concept again is sticky assignment. The word incremental means rebalance partition one by one. And that is all for consumer-induced rebalance. Most of the time, if you are talking to an application developer, that is the only rebalance they talk about. But there's another rebalance on the broker side. Sometimes people call it cluster rebalance. Application developers don't talk about it because this has nothing to do with consumer at all. It is completely within the cluster. So what is cluster rebalance? The trigger is a change in cluster membership. It happens when you scale the cluster. It means you add or remove broker machines. Then we need to move partition ownership from one broker to another. Now this involves physical data migration. When you spin up a new broker, that broker has no data at all. So it needs to get data from one of the existing brokers. Hence the physical data migration. I quote from Kafka Improvement Plan 405, Kafka tiered storage. When a new Kafka node is added to scale the cluster, cluster rebalancing assigns partitions to the new node, which requires copying a bunch of data. So this is from network. This can eat up your network bandwidth. The recovery time is proportional to amount of data stored on a Kafka local broker. So reducing the amount of data on each broker can reduce the recovery time. Imagine if your partition have hundreds of gigabytes of data, that data needs to be streamed over the network to your new broker machine. That can take quite a bit of time. So can we avoid rebalance altogether? The consumer side rebalance is inherent to load balancing problem, so that's unavoidable. But the broker side rebalance can actually be avoided. Since Kafka 3.6, there's a new feature called tiered storage. If you take a look at the release blog of Kafka 3.6 by Confluent, it contains the Kafka tiered storage KIP 405, which I discussed earlier. So how does tiered storage solve the cluster rebalance problem? On a high level, don't store your partition data locally, store it remotely. A broker will have its own local hard disk, but with minimal amount of data with some retention period. And for the older storage, it will rely on remote. So when you spin up a new broker machine, you only need to rebalance part of the data. Majority of the data is already in remote. The high-level concept is called separating compute and storage. Previously, broker does both compute and storage. Compute means serving the client request. Storage means store the partition data. When compute and storage are bundled together, you are over-provisioning resources. It's not cost-effective. When you separate the two, your broker now can optimize for compute, meaning have less disk space, and optimize for memory and CPU. And for your remote storage, you can dump your data on S3. You can optimize for disk space and less CPU and memory. So that is more cost effective. Finally, the takeaway. Partition is the unit of data distribution. It means the data is split logically and physically. It is also a unit of parallelism. The more partition you have, the higher the throughput. Consumer-side induced rebalance can be alleviated with incremental cooperative rebalance protocol. Partition configuration is mostly static for the lifetime of an application. Cluster rebalance can be avoided by separating compute and storage.